As you can see on the bottom left, this is the reflex which happens, which causes the muscles to like shorten and contract. For example, the receptors in the skin will receive some information like change in environment, and then through the sensory neuron, it will go to the central nervous system, such as the brain and spinal cord, which they'll be informed of the need in changed muscles, and then this travels through the relay motor neuron, and then down from the central nervous system through the motor neuron to the muscles, where they will be caused to change. Here is a sheet of different plyometric exercises for high intensity exercise, and to summarize, this adaptations will cause increased hypertrophy, tendon strength, glycogen stores, triglyceride stores, myoglobin stores, mitochondria, and neural pathways. Now, in terms of energy system adaptations for anaerobic training, glycolysis is the breakdown of glucose, and the aerobic glycolytic system produces a lot of power. By around 30 seconds of sustained activity, the majority of energy comes from the anaerobic glycolytic system. At 45 seconds of sustained intense activity, there is a second decline in power output. Exercise beyond this point has a growing reliance on the aerobic energy system, as the anaerobic glycolytic system starts to fatigue. High intensity training such as sprints, weights, plyometrics, etc., adapts the body so that the anaerobic glycolytic system can be sustained for a longer period of time. A further adaptation is the ability to deal with the buildup of lactic acid in the blood system. This is called onset of blood lactate accumulation, or OBLA. Once lactic acid reaches a certain point, the body's ability to produce energy decreases. Anaerobic exercise adapts the body to deal with higher levels of lactic acid, and therefore train or compete for a longer duration and at a higher intensity. A key indicator of the body's energy system adaptations can be measured through basal metabolic rate, which is BMR. This is a measure of the number of calories required to keep the body functioning at rest. Through anaerobic training, the body muscle mass increases, and fat reduces, and the metabolic rate increases. This means that the body burns more calories, which in turn raises the body's BMR. Anaerobic exercise such as weight training, sprinting, and fast swimming and boxing raises the body's BMR. By calculating the BMR, an athlete can accurately work out how many calories they burn and how many calories they need to consume to maintain certain levels of exercise intensity. As you can see on the graph at the top, straight away there's a really high level of ATP energy. However, this only lasts literally a few seconds, and so suddenly decreases, and then there is no ATP left. Then the next store used will be glycolysis, and this raises gradually around 30 seconds, and then it rapidly decreases as it's used up. And however, oxidative energy increases rapidly, and then it sort of levels off at around 85 of total energy. These adaptations cause increased enzymes, uses of fats and energy source, lactic acid tolerance and buffering, OBLA, glycogen stores, and ATP to PC stores. Now for the skeletal system. The body's skeletal system adapts and responds to resistance training such as plyometrics, HIIT, and weight-bearing exercises such as specific circuit exercises and weight training. The main adaptations are to do with building strength and bone density. Resistance and strength training builds stronger bones through stimulating new bone growth. Osteoclasts destroy areas of older bone, and then osteoblasts start to lay down collagen and other materials in the area that have been destroyed. These then turn into osteocytes, which are bone cells that form new bone. The bones uptake minerals and calcium and strengthen them to make them harder, and therefore they're less likely to damage during exercise. Strength training exercise also improves the strength and flexibility of the joints. This is seen by the elbow joint in the bottom of the page. An increase in collagen makes the cartilage thicker and the joint less prone to injury. The increase in collagen also strengthens ligaments that connect bones and muscles, and they become more resistant to straining and strain through exercise. Range of movement and bone health is developed through exercise. Exercises that are good for this include swimming, yoga, Pilates, and circuit training. Active range of motion exercises help to improve joint function and how far joints move in different directions. These exercises help move each joint through its range of motion. Movement can help your joints flexibility, and be flexible, reduce pain, and improve balance and strength. Bones are living tissues that destroy and regenerate all the time. As people get older, it is more important to strengthen bones, to maintain a good posture, strength, and to reduce the possibility of developing bone related diseases such as brittle bone disease. Stronger bones are harder to break, but unfortunately as we get older our bones do just naturally get weaker as we don't exercise them as much. This adaptation causes increased calcium stores, collagen and tendon strength of ligaments, and cartilage thickness and osteoblasts. Now for neuromuscular system adaptations of aerobic. So aerobic training increases the muscular endurance of muscles that are utilised in training and during events. This is especially important for athletes who participate in longer duration events such as half or full marathons. For a cyclist, the main muscles that would adapt to the training would be the thighs, quads, calves, and hips. Whereas a swimmer would have a contrast and the muscle adaptations occurring in both the lower and upper body, as these muscles are involved in developing the most efficient stroke. Adaptations to the muscles promote the uptake and utilization of oxygen and the increase in energy that is supplied through the aerobic energy system. One of the key adaptations is the production of myoglobin. During exercise, the amount of oxygen supplied by the blood is not sufficient to meet demand. However, myoglobin stores oxygen, which is released during exercise and increases the amount of energy supplied. Muscular endurance exercise, such as weight training, circuit training, plyometrics, and HIIT training, are all improve the stores of myoglobin in the muscles. A further adaptation is the increase in the amount of mitochondria in the muscle tissue. The mitochondria takes in the nutrients from the cell, breaks it down through respiration as it takes in oxygen as well, and turns into energy. The more mitochondria that the athletes have, the more in their muscle tissue, the more energy can be produced through aerobic exercise through a good supply of oxygen. Aerobic exercise promotes adaptations in different muscle fibers. Slow twitch fibers, called slow oxidative fibers, are utilized by endurance athletes in long distance races such as swimming a 400-meter race. A cyclist completing a stage of the Tour de France, or a marathon runner. These muscle fibers have a large amount of mitochondria myoglobin. These muscle fibers contract slowly and do not tire or fatigue as quickly, and therefore provide an athlete with a more sustainable source of energy. The other types of muscle fibers that adapts through aerobic exercise is called the fog fibers, which are fast oxidative glycolytic fibers. So, like slow oxidative fibers, they have large amount of mitochondria and myoglobin. They also generate high amounts of ATP, which is converted to energy. Development of these muscle fibers is especially beneficial for a 1,500-meter runner or a fast 5K runner who needs fast release of energy but is able to sustain a pace without quickly tiring. For energy system adaptations for aerobic exercise, aerobic exercise and training increases the level of ATP and glycogen in the muscles, which in turn provides athletes with improved and sustainable sources of energy. Aerobic enzymes in the muscles produce energy through making the ATP. By increasing the number of enzymes through aerobic adaptations, the more ATP can be produced. As a consequence of this, longer duration athletes has more sustainable sources of energy. An increase in the amount of aerobic enzymes also leads to an increase in the amount of mitochondria, which, as discussed earlier, provides increased energy supply. A further adaptation in the energy system that can be developed through exercise is glycogen sparing. Glycogen is the main energy provider during exercise intensity above 70% of maximum heart rate. This high aerobic state would be experienced towards the end of a fast 5K run or 1,500-meter race, and fatigue develops when the glycogen stores are depleted in the active muscles. Glycogen sparing is where the muscles store glycogen as reserves to be used once the main supply of glycogen has been used up. One further adaptation is the ability for the muscles and blood to cope with the buildup of the lactic acid during intense exercise, and the lactic acid buildup in the bloodstream. When this reaches 4 times its normal limit, the body's normal energy system does not work efficiently. OBLA is the point where the muscles can no longer get rid of lactic acid and the pH levels of the blood decreases. Training at higher intensities such as circuit sprints, hill reps, and HIIT encourages the body to work at an anaerobic rate, which the body adapts to and is able to function longer with higher concentration of lactic acid. Endurance and highly trained athletes can reach an OBLA at 85% of VO2 max compared to 40% for the average person.